One reaction proceeds through a cationic intermediate, and that intermediate determines its stereochemical outcome to a large extent because it's planar and achiral. In E2 reactions, we don't have any intermediates, and therefore its stereochemical outcome is much more controlled by the transition state. And now we will see what transition state is optimal for stereochemical E2 reactions and what stereochemical outcome it leads to. A particular instructive example to look at would be a cyclic system, such as this one, which is also fixed in a single conformation by the presence of this T-butyl group, which prevents ring flipping. If we look at the cis isomer of this compound, then exposure of this isomer to base will lead to the fast formation of this alkene product. On the other hand, if you look at the trans isomer of the same compound, then this trans isomer will only very slowly react with base to give us the same alkene. Trans and this is cis. Why is this? The answer lies in the orbital arrangement of the groups involved in the E2 reaction right before departure. So what our material, our cis material has is this so-called anti-periplanar arrangement between the bromide CC bond and CH bond. And this antiplanar arrangement is productive since the base can tag this hydrogen and simply enhance this interaction that is already sort of in its infancy here between the bottom small lobe between the CBR bond and the large lobe of the CH bond. Okay? In the case, so antiperiplanar simply means they're in the same plane, but opposite in the opposite directions from each other. And this is a normal staggered anticonformation, as we've seen in butane. So, but in the case of our trans isomer, then our CBR bond and our CH bond, regardless of which CH bond we look at, they're not going to be anti, they will be gauche, which means that there will be no overlap between them since they're not in the same plane. And that's why this reaction proceeds significantly slower. In acyclic systems, this leads to important consequences in terms of the stereochemistry of alkenes, because in acyclic systems rotation is free. So if we have something that looks like this, and we have our hydrogen here, then the base will attack from this side, strike this hydrogen, form a double bond here, and we will preserve the relationships that we already had, right? Because we already had the system positioned in the anti-orientation. So then we would get the cis isomer with two metal groups on the same side. Okay, so this reaction is another example of a stereospecific reaction. Because if we start with a certain starting material, starting stereoisomer, we'll get certain stereoisomer. If we start with a different stereoisomer, we'll get a different one. So that two different stereoisomers lead to two different products. This requirement for anti-periplanar stereochemistry is sometimes violated. An example would be a case of this bridgehead system, which was isotopically labeled, so that we have deuterium here and hydrogen here. Of course, deuterium and hydrogen behave identically in terms of the chemical properties, but they serve as sort of useful labels to the course of the reaction. So in this case, what we saw is that after we expose this species to base, we observed this DH product, which means that this hydrogen and this bromide were eliminated. And they certainly were not in the anti-periplanar conformation. In fact, if we draw this out, we will see that they're in exactly the same plane, but they're the so-called syn periplanar conformation, which means that they're eclipsing each other, but that they remain in the same plane. Now you might say, well, eclipsing interactions are unfavorable, so why would this happen in the first place? The reason for that lies is that this bridgehead compound already overcame its unfavorable eclipse interaction. The compound is already there, and it has to have eclipsing interaction. It's not stable, but since it's already formed, it's there. And so these eclipsing interactions now can be used productively in our elimination reactions. However, the syn periplanar arrangement is observed much less frequently. Than the anti. So in summary, the E2 reaction, unlike E1, is stereospecific. It gives you the more stable, more substituted alkene, but it gives the one which results from the anti-periplanar transition states in which the leaving group and the hydrogen that is going to be abstracted by the base are positioned in the anti-staggered interaction. In some rare cases, such as this one, syn periplanar interaction would work as well. But the important point is that we need two groups, the hydrogen and the leaving group, to be in the same plane, either anti or syn, for this reaction to occur. In the final topic of this lecture, we will compare the four reaction mechanisms that we already seen haloalkanes are exposed to, the E1, E2, SN1, and SN2 reaction.